This paper, titled, Nanoporous Block Copolymer Membranes with Enhanced Solvent Resistance via UV-Mediated Cross-Linking Strategies, presents a study on the synthesis and characterization of block copolymer membranes with improved solvent resistance. The authors focus on a specific block copolymer, BCP, consisting of poly-butyl methacrylate co-benzophenone methacrylate co-methyl methacrylate, block 2-hydroxyethyl methacrylate, BMA co-BPMA co-MMA, BP, HEMA, and its fabrication into nanoporous membranes using the self-assembly and non-solvent-induced phase separation (SNIPS) process. The introduction begins by highlighting the growing interest in polymer membranes for separating components from water or organic solvents. The authors emphasize the importance of nanoporous membranes, which feature pore sizes in the range of 5 to 100 nanometers, for various applications such as wastewater treatment and selective separations. They note that BCPs are an exciting class of polymers for creating nanoporous films due to their ability to form well-defined and adjustable pore sizes. The authors explain that the fabrication of BCP membranes typically involves a combination of self-assembly and non-solvent-induced phase separation processes. They provide a brief overview of the SNIPS process, wherein a concentrated polymer solution is cast on a support and immersed in a non-solvent bath to induce microphase separation and form a selective layer with uniform pores at the top of the substrate. The introduction also discusses the challenges associated with the structural change and lack of long-term stability in BCP membranes. To address these issues, the authors propose UV-mediated cross-linking strategies for stabilizing the membrane structure. They highlight previous studies that have utilized UV-induced cross-linking to enhance the stability of BCP architectures, such as micelles and capsules. The authors then present their specific approach to fabricating UV cross-linkable BCP membranes. They describe the synthesis of the BCPP, BMA co-BPMA co-MMA, BP, HEMA, using a two-step atom transfer radical polymerization (ATRP) procedure. They explain that the incorporation of benzophenone methacrylate, BPMA, as a UV cross-linkable monomer allows for the formation of cross-linking sites within the matrix-forming block segment of the membrane. The introduction concludes by stating the objectives of the study, which include investigating the swelling capability of the non-cross-linked and cross-linked membranes in different solvents, evaluating the influence of cross-linking on water flux measurements, and exploring the potential of UV-mediated cross-linking for the development of stabilized membranes in separation technologies. In this figure, the authors present the analytical data for the block copolymer BMA co-BPMA co-MMA, BP, HEMA, P2. The molecular weight distribution of the macroinitiator P1 and the block copolymer P2 is shown using size exclusion chromatography, SEC. The SEC traces indicate a clear shift to higher molar masses for P2 compared to P1. The authors also analyzed the chemical composition of P2 using 1-HNMR spectroscopy. The molar fractions of the different polymer components were calculated based on the corresponding integrals from the 1-HNMR spectrum. The results show that the amount of the UV cross-linking agent BPMA is approximately 10 mol% within the macroinitiator P1, while the hydrophilic block HEMA, is determined to be 10 mol% for the overall block copolymer P2. The molecular weight, polydispersity, and composition data of P2 are summarized in Table 1. Overall, the analytical data confirm the successful synthesis of the desired block copolymer with the desired composition and molecular weight. This figure shows scanning electron microscopy, SEM, images of the nanoporous block copolymer membranes fabricated using the self-assembly and non-solvent-induced phase separation, SNIPS, process. The topographies of the membranes exhibit an open porous surface structure with pore sizes of 26 ± 5 nanometers and 30 ± 5 nanometers for membranes prepared with 10s and 15s evaporation times, respectively. Cross-section SEM images of the membranes reveal a sponge-like substructure, characteristic of integral asymmetric block copolymer membranes. These images confirm the successful fabrication of nanoporous membranes with a porous top layer featuring uniform pores. The pore sizes obtained from the SEM images are consistent with the desired pore sizes for ultrafiltration applications. This figure presents the solvent dependency of the pore sizes of the cross-linked and non-cross-linked block copolymer membranes. Atomic force microscopy, AFM, images and histograms of the maximum inscribed radius ERM are shown for air, water, ethanol, 1,1, and ethanol environments. The results indicate that the distribution of the pore sizes is shifted to smaller values when the membranes are immersed in water or ethanol compared to the air environment. Furthermore, the pore sizes are smaller in the water-ethanol mixture compared to pure water, indicating a further reduction in pore size due to the presence of ethanol. The cross-linked membranes exhibit smaller pore sizes in all solvents compared to the non-cross-linked membranes. These findings demonstrate the stabilizing effect of UV cross-linking on the porous structures of the membranes, leading to increased swelling resistance. The pore sizes determined from the AFM images are summarized in Table 3. The authors of this paper developed a nanoporous block copolymer membrane with enhanced solvent resistance using UV-mediated cross-linking strategies. They synthesized an amphiphilic block copolymer consisting of poly-butyl methacrylate co-benzophenone methacrylate co-methyl methacrylate, block 2-hydroxyethyl methacrylate. The membrane was fabricated using the self-assembly and non-solvent-induced phase separation process and showed a porous top layer with pores of about 30 nanometers. The authors then optimized UV-mediated cross-linking protocols to maintain the porous structure of the membrane. They found that the cross-linked membranes exhibited increased swelling resistance in water-ethanol mixture, and pure ethanol compared to the non-cross-linked membranes. Additionally, the cross-linked membranes showed higher water flux compared to the non-cross-linked membranes. These findings suggest that the UV-mediated cross-linking protocol can enhance the stability and performance of nanoporous block copolymer membranes, making them promising candidates for separation technologies. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.